Hello friends, myself Rohit Kumar Wagdarikar, working as an assistant professor in Computer Science and Engineering Department, Walchand of Technology, Solapur. Now today we are going to discuss on the interprocess communication and synchronization. The learning outcome of this session is at the end of this session the students will able to understand the concept of interprocess communication and synchronization, basically which includes the race condition, mutual exclusion and the semaphore. Now first we will understand what is actually the process. Now when the program is come into the RAM for the execution purpose, or we can call it as a program is in execution phase or state, at that time we can call it as a process. Nowadays we'll have many high-end computer systems which have high-end operating systems. Means what? These operating systems will perform the concurrent and parallel execution of the process. Now while performing this parallel or concurrent execution, many threads needs to communicate with each other. So now to perform this communication, and by doing this communication they can perform the multi-programming, multi-processing and distributed system and client server model computations. Now this concept is we can call it as a interprocess communication. Now there will be the three different types of the process. Now the first one is competing process. Process themselves do not share anything, but operating system has to share the system resources among this process, competing for the system resources such as disk or the printers. For example, now we'll have the n number of processes and these processes wants to use some resources. At that time they are competing with each other to get that resources. That is called the competing process. Now another one is a cooperating process. This cooperating process result, one of the process gives the input to the another process. Now second one is a cooperation by sharing. The cooperation by sharing is an example of input output buffer, now which includes the concepts of the critical section, and this communication we can call it as an indirect communication. And the third one is cooperation by communication. Example, typically no data sharing, but coordination through the synchronization becomes the essential in certain applications. That we can call it as a direct communication. Now these are the three different types of the process. Now interaction between process. Computing process are the system level process. Its problem is deadlock and starvation. Means when this computing process request for some resources and that resource is already held by some other process, now at that time that systems came into the deadlock state. This thing we have already seen in the previous video. And the cooperation by sharing are at the process level and its problem is the mutual exclusion, and cooperation by communication are the process levels. Now here we'll see the race condition. Race condition is a situation where several processes access and manipulate shared data concurrently. The final value of the shared data depends upon which process finishes the last. For example, just consider we'll have the two processes and these two processes currently executing on a concurrent operating system. Now here just one take like one variable or buffer A which has stored some value 10. Now when process 1 comes for the updation purpose, means he is going to write some data on that buffer. Now what it will do, he will first write some data onto the A and same buffer or shared data is going to be shared by the process P2, and after P1 process 2 is again accessing that shared value and making the modification, it means performing the write operation on it. And now after that the third one, when process P1 comes for the reading the value, last time he has wrote value is now replaced by the P2's value. Now that condition is called the race condition. Means the process which finishes last will have the final value. To prevent this race condition, the concurrent process must be proper synchronized. That is called the race condition. Now here we will see the mutual exclusion. A mutual exclusion is a program object that prevents the simultaneous access to a shared resources. This concept is used in the concurrent programming with a critical section. Now here the critical section is a piece of code in which process or thread access the shared resources. Only one thread owns the mutex at a time. Thus a mutex with a unique name is created when a program starts. When a thread holds the resource, it has to lock the mutex from other threads to prevent the concurrent access of the resources. Upon releasing the resource, the thread unlocks the mutex. Means what? In this mutual exclusion, it's one program or one object or one module in which at a time only single process can enter into the critical section. And now, when that process will enter into the critical section, at that time, he will first need to lock that critical section and enter into the critical section. After completion of his task, it will unlock the critical section and come out of the critical section so that other process can demand for the critical section. Now this will be happen with the mutual exclusion, and we can implement these mutual exclusion concepts with the help of mutex. Now one more technique is here, the semaphore. Now here we have given one small statement on the critical section. Basically this critical section is a code segment which is executed by a single process at a time. Now as we have last time told that critical section, into the critical section at a time single process can enter. Now semaphore is simply a variable. This variable is used to solve the critical section problem and to achieve the process synchronization in the multiprocessing environment. Now here we have already seen, to solve the critical section problem we need to perform the mutual exclusion, right? So now here the two most common kind of semaphores are counting semaphore and binary semaphore. Basically the counting semaphore and binary, out of this binary semaphore, the binary semaphore can take the value, or we can call it as it will work only on the 0 1. It means it has only a single resource. Now here I have given one example like the washroom example. Now at our home or in any public sector we'll have some washrooms. In that washroom at a time single person can enter. The same concept here we can apply as an example. Now for example, I want to use this washroom. At that time first of all I'll open the washroom door and I'll lock it, I'll use the washroom and then I'll unlock it. Means the process P1 is first of all entering into the critical section, lock it, while coming it will unlock it. Now when at that time when the P1 is inside the critical section, at that time that the door of the washroom is locked, means already one process inside the washroom, or we can call it as a equivalent for it is critical section, as an example we have taken. Now the next one is continuous semaphore. Here it's a counting semaphore can take the non-negative integer value. It means the system has the n number of resources. Example, the receptionist on the lodge counter. When we go for the any on trip or somewhere else, now if we are going to take one room on rent basis, on per day basis, or we'll visit on the lodge or motels, at that time there will be so many rooms are available. So now to get the which room is vacant, we need to look at the counter. We'll ask the counter receptionist which room is available. So at that time we look into the board. If the key is available, it means that room is vacant. The same thing here we have applied. Here in the counting semaphore will decrement the values when actually the resources are going to be used. So these resources are shared among the multiple processes. So it is basically a synchronizing tool and is accessible through two low standards atomic operations called the wait and signal, that is designed by P of S and V of S respectively. Means To implement this semaphore, we need to use the two functions, wait and signal. The wait basically decrement the value of its argument as soon as it would becomes the non-negative integer. Means if it is in the counting semaphore, then we have n number of resources. When I'll use one resource, at that time I'll decrement the resource. Now when I'll release the resource, at that time I need to increment into the resource count. So at that time I'll execute the signal. Now here the signal function increment the value of its argument as there is no more process block on the queue. Now just look at this example. Here we'll have n number of, here we'll have the mutex and we'll have the semaphore variable which have the 1. It means we are going to implement the counting semaphore, binary semaphore. Now here process I starts and here it needs to enter into the critical section. At that time it will execute the p of mutex, means first it will decrement the value of semaphore by 1. Now the value of semaphore becomes 0. Now it will enter into the critical section and after completion of a task it will execute the v of mutex, means it will again increment the semaphore value, or we can say the mutex value. Now it becomes again 1. So now here, how can we achieve the synchronization in concurrent processing? Now the answer is by using mutual exclusion and semaphore. Now the references, we got this material from the operating system concept by the Galvin and system program and operating system book by the Dumdere, and we have already mentioned in the last video, like we have used some YouTube channels and we have used some papers also. Thank you.